welcome to this explainer. Today, we're going to absolutely demystify the complex, super fast-moving world of large language models. But we're not just looking at what these models do right now. No, we're actually going to trace their evolutionary roots. Think of this as, well, the family tree of modern AI. And honestly, once you understand this family tree, it is going to completely change how you view the technology that we all use every single day. Let's get into it. Here's our roadmap for today. First up, the original transformer. Then, encoders and deep bidirectional context. After that, the evolution of BERT. Then we'll hit SBERT versus cross-encoders. And finally, decoders and autoregressive text generation.
All right, let's start with Section 1, the original transformer, the common ancestor.
Okay, so cast your mind back to 2017. This massive, absolute game changer of a paper drops. It's called Attention is All You Need, and it introduces a whole new paradigm for processing sequences in parallel, literally changed machine learning forever. But here's the fascinating part. It introduced this complex architecture that wasn't just some single, uniform block. Actually, it was a combination of two halves working really closely together. You've got an encoder block on the left and a decoder block on the right. They were bolted together specifically to conquer those really complex sequence-to-sequence translation tasks. Just to appreciate the sheer magnitude of this early model, just look at this number, 213 million parameters. Wow. I mean, to put that into perspective, it required 3.5 days of non-stop intensive training across 8 incredibly powerful GPUs. It was crunching through 4.5 million sentence pairs just to learn how to successfully translate English to German. At the time, this was the absolute state-of-the-art benchmark. But to figure out where AI went next, we really have to break down the roles of those two distinct halves. So think of encoders like meticulous detectives, right? They process an entire input sequence all at once. It's like they're analyzing the entire crime scene simultaneously to capture the deep underlying contextual relationships of every single clue. Decoders, on the other hand, well, they're more like improvisational actors. They generate output tokens one by one in what's called an autoregressive manner. Basically, they're building a story step by step based on the patterns they've learned and whatever the encoder is feeding them.
Now, this brings us to a really pivotal question. It's kind of the catalyst for the rest of this explainer. If that original translation model used both of these halves, do we actually need both components for every single task? The short answer? No. No, we don't. And honestly, that exact realization is what splits AI history right down the middle into two completely distinct branches.
Which leads us to Section 2. Encoders, deep bidirectional context.
So researchers had this wild idea. What if they just threw away the text-generating decoder half entirely? By doing that, they could focus a model purely on deep understanding. By isolating just that encoder side, we got models like BERT. You can think of them as the deep reading scholars of the AI world. Instead of generating new text, an encoder-only model processes all the tokens simultaneously. It learns through this totally fascinating, self-supervised process called masked language modeling. Basically, imagine randomly hiding about 15% of the words in a massive book, and then forcing the model to guess the blanks using the words on the left and the right. Because it relies on this two-way, bidirectional context, its comprehension becomes incredibly deep. It's absolutely perfect for feature extraction and classification, rather than, writing a poem. In fact, this deep comprehension is exactly why these models are so ridiculously good at understanding the true intent behind your search engine queries.
Moving on to Section 3, the evolution of BERT.
Okay, so once the researchers established this incredibly powerful encoder branch, it didn't just stop there. It rapidly evolved to handle all sorts of specific computing needs. We get this awesome iterative evolution. Step 1, of course, was the original BERT. Undeniably powerful, sure, but man, it was computationally expensive. That led to Step 2, Roberta. See, the researchers realized that an original training step called next sentence prediction was actually pretty ineffective, so Roberta just scrapped it, trained on 10 times more data using dynamic masking, and boom, achieved higher accuracy. But it demanded even more compute power. So finally we arrive at Step 3, DistillBERT. This used a super clever process called knowledge distillation. It's essentially like a teacher model training a smaller student model, stripping down the architecture to create something much lighter and way faster.
And check this out. DistillBERT manages to retain a staggering 95% of the original BERT model's accuracy, while dropping 60% of the parameters and running 60% faster. I mean, that's a massive win-win. It just goes to show that as these models evolve, they can become vastly more optimized for real-world use. Frankly, it's the exact reason advanced AI can actually run locally, right there on your phone, without completely draining your battery in 5 minutes flat.
All right, Section 4.
SBERT versus cross-encoders.
As we reach the very tips of this encoder branch, we run into a really crucial trade-off. Here's the thing, standard BERT, it is surprisingly inefficient at comparing sentences because it processes them totally independently. So to solve that, the evolutionary branch split once again. On the left side, we have SBERT, or sentence BERT. It encodes sentences separately into fixed vectors, which allows for blazing fast similarity searches using basic cosine similarity. But over on the right, we have cross-encoders. These jointly encode both inputs together. Now that achieves much higher accuracy for complex ranking tasks, but it is vastly slower. And let's be real, none of us want to sit around waiting 10 seconds for a search result to load, right? So in practice, modern systems actually use both. They'll use SBERT to grab lightning-fast initial results, and then they'll use cross-encoders to perfectly rank those top few hits. It's a really brilliant combo.
Okay, on to our final section, Section 5, Decoders, Autoregressive Text Generation.
So up until now, we've really been looking at deep, precise understanding. But now, let's pivot all the way back to the trunk of our evolutionary tree and follow that second massive branch, the decoder-only models. Now, if you want to understand models like the famous GPT series, we absolutely have to grasp this one specific term, autoregressive. It sounds complex, but it just means generating text sequentially, token by token, where every single new word is conditioned on all the previously generated words. It perfectly describes those improvisational, fast-talking storytellers we talked about earlier, literally just building sentences step by step.
Unlike those deep-reading encoders, these decoder models strip away everything else to specialize purely in open-ended text generation. And here is the absolute defining characteristic. They use what's called causal or unidirectional self-attention. Basically, that just means they only look backward. They physically cannot peek at future words while generating their outputs, and they don't generate full sequence embeddings all at once like BERT does. No, they are purely 100% focused on predicting what comes next over and over and over again.
Honestly, understanding this fundamental split between the deep-reading, context-heavy encoders on one side and the fast-talking autoregressive decoders on the other, that gives you the literal blueprint to all modern AI architecture. It's amazing. We started with this one dual-natured ancestor back in 2017, and it evolved into these highly specialized species that literally power our world today. Which really just leaves us to wonder, as we watch this blistering pace of AI research unfold, what entirely new architecture, what radical mutation is currently waiting to blossom on the very next branch of this evolutionary tree?